Alright, for number 3, we're going to go ahead and find our critical values by taking the derivative and figuring out when it's equal to 0 or when it does not exist. So when taking the derivative here, we could actually make this a little bit easier on ourselves. Let's go ahead and actually rewrite what this is equal to. In this case, since there's no exponent out here, let's distribute this. We have 8x to the 2/3 minus x. This is x to the first, so we can add these exponents. So 2/3 plus 1 gives us 5/3. So we can go ahead and take the derivative of this function. Instead of having to use product rule, we can do the product first and then take the derivative. So if we bring the 2/3 out in front, we get 16/3 times x to the negative 1/3 minus derivative of this, we've got 5/3 x to the 2/3. We can factor out an x. I'm going to go ahead and factor out a 1/3 times x to the negative 1/3. We can factor out the smallest exponent. By factoring out the 1/3, we also take care of that fraction out. And if we divide these, 16/3 divided by 1/3, that's just going to be 16. And these divide to give us 1. So all we're left with is 16 there. Negative 5/3 divided by 1/3 is negative 5. And we're subtracting the exponents when we divide these, so we get negative 5x. Well, we can write this with positive exponents. We get 16 minus 5x over 3 from the 1/3 times x to the positive 1/3. Or we can think of that as the cube root of x. So we can figure out our critical values by figuring out when is the derivative equal to 0 and when is the derivative not exist. So let's figure out when it's 0 first. We can put in 16 minus 5x, set that equal to 0. Because if that numerator is 0, that's going to make the whole thing 0. So negative 5x equals negative 16. X equals 16/5. So that's one critical value. And for values there where the derivative does not exist, we're taking the denominator and setting it equal to 0. So 3 cube root of x, we want to know when is that 0, because that would make the whole derivative not exist. We can divide both sides by 3. We get cube root of x equals 0. We can cube both sides, so x would have to be 0. That gives us two critical values for our number line. We have 0 and 16/5. So our derivative is equal to 0 at each of these values. And we want to figure out what the derivative is in between and on either side of these. So let's figure out what the derivative is when x is negative 1. Here's our derivative. We put negative 1 on top. 16 minus 5 times negative 1. We're going to get a positive value. Bottom, the cube root of negative 1 is negative 1 times 3, so we get a negative value. Positive divided by negative is going to be negative. And I just realized a mistake that I made when labeling this number line. Here the derivative is equal to 0, so at 16/5 the derivative is 0, but when x is 0, that's when the derivative does not exist. So instead of putting 0 there, I'm going to put a u for undefined, because that makes a difference in what our graph looks like. We'll talk about that in a little bit. Now in between here, we can find the derivative when x is 1. Top is still going to be positive if we put a 1 in for x, but now the bottom is also going to be positive. So we get positive derivatives in between 0 and 16/5. And for the last one here, I'm going to put derivative of 4. We're going to put 4 in here. 16 minus 20, that's going to give us a negative value. And cube root of 4 is going to be positive times 3 is positive. So we have a negative divided by a positive, which gives us a negative. From our number line, we can determine that these 2 points our local mins and maxes. This one, since it's decreasing then increasing according to the slopes, is going to be a local minimum. Here, this is increasing then decreasing, so this one's going to be a local maximum. Right? Derivative tells us the slopes. We have a negative slope, then positive slope. Negative, then positive. Positive, then negative. That tells us our local extrema. Now, for our graph, we're going to plot those points, but we also have to keep in mind this undefined here, since it's changing direction, what's happening here is it's going to have a sharp turn. Right? It's going to have a sharp turn in order to be undefined, because that means that the left-hand derivative and the right-hand derivative are not going to be equal in this case. If this was going from negative to negative, we would have a vertical tangent line. But since it's changing, it's going to be a sharp turn. When the derivative is 0, it's going to be a smooth turn. So we have to keep that in mind when we're drawing this. 2 points we do need to plot are when x is 0 and when x is 16/5. So we're plugging those into the original function. Right? We want to find the points on the original graph. If we put 0 in there, we get 0 out. If we put 16/5 in here for x, we end up getting about 10.423. Again, just by plugging it into the original function. So we end up with 0, 0, and 16/5. So that's like 3.25, 10.4. So it's just going to be a little bit off the graph here. And now we have to look at this again. Remember, it's decreasing. The graph is going down until we get to this sharp turn at 0. Then it increases until we get to 16/5, makes a smooth turn and goes down. So down, up, down. But remember, this is going to be a sharp turn. So as we come down here, and then we're going to have a sharp turn that goes up here, do a smooth turn, and back down. Right? Negative slope, sharp turn, positive slope, smooth turn, negative slope.